Hello, my name is Paul Geyer, and I'm here to chat with you today about passive solar buildings. This is what I'll be talking about today, sort of the chapters in the book, if you will, some introductory comments, then I'll talk about systems for utilizing solar energy passively to heat buildings. Heating a building, by the way, is just about, from a practical standpoint, the only thing that you can do with solar energy passively. I'll be talking about the systems and then about climatic considerations, because climate is a very important consideration in determining the feasibility of passive solar heating at your project. And then I will be concluding with some kind of random rules of thumb or sources of additional information, that sort of thing. By way of introduction, this is a little bit about me, what I've been doing for the last few decades. Got registered in a few things along the way. I've always been a designer, broadly based designer, and I got registered, as I say, in a few different things, but I'm basically a mechanical engineer. That was my degree in my first registration. This discussion is intended as an introduction to the principles and concepts underlying the design of buildings to passively utilize solar energy for heating. Here are some points for you to keep in mind as you go through this material. It's an introduction to the passive solar technology that may be used to heat buildings. It is not about active technologies. Usually an optimal solution for a specific building and locale involves passive technology supplemented by active technologies. Active technologies are not part of this discussion. Passive technologies are. This will be discussed further. Utilization of passive solar energy to heat buildings is fundamentally an exercise requiring an understanding of, first, the fact that heat is transferred from outside to inside a building, or vice versa, by conduction, convection, and radiation, and secondly, the concept of heat sinks as a reservoir for heat storage. The procedures for design of buildings to passively utilize solar energy for heating buildings may typically involve use of shading devices to reduce heating by radiant, that is solar energy, in the summer and to allow it in the winter. Utilizing thermal convection, i.e. the fact that hot air rises, cold air sinks, to maximize heating by convection in winter. And third, utilizing thermal storage, the mass effect, to transfer excess heating capacity from daylight to nighttime hours. This is an introductory discussion. It's intended to tell you about the basic systems and climate considerations underlying the passive utilization of solar energy to heat buildings. It's not intended to be a definitive design manual that can be used for feasibility studies, design analyses, and building design. There are 6 basic types of passive solar systems for buildings: direct gain heating, daylighting, radiant panels, thermosiphoning air panels, thermal storage walls, and sun spaces. Another important consideration is what is referred to as incremental cooling load. Now the basics. The mechanisms by which heat is gained or lost by a space are 3: conduction, convection, and radiation. The first of the systems that we will discuss is direct gain heating. Direct gain buildings are passive solar heating systems in which sunlight is introduced directly to the living space through windows or other glazed apertures, as indicated schematically in Figure 1. As with all passive solar systems, it's important that the apertures face south or nearly south in order to achieve high solar gains during the winter heating season and low solar gains during the summer cooling season. Figure 1 indicates schematically the key elements of a direct gain heating system. You have the south-facing apertures, that is windows. You have the double glazing or triple glazing on those windows because you want to benefit from the radiant heating from the sun passing through the window, but you do not want to then lose that heat by conduction if you have a poorly insulated south-facing wall. And with glass, a single pane of glass, single sheet of glass is a very poor insulating material. And to have a good insulating value on those south-facing windows, you have to use double or triple glazing. You also see the overhang indicated schematically. Then there is the thermal storage mass, which can be the floor slab and the walls that are non-south facing. And then you have external insulation, and of course the purpose of the insulation is to minimize the amount of heat that is lost from the interior of the building to the exterior. Thermal storage mass is essential to the performance and comfort of direct gain buildings. A building that has inadequate mass will overheat and require ventilation, which entails a loss of heat that might otherwise have been stored for nighttime use. Generally, it is desirable to employ structural mass as a storage medium in order to take advantage of the improved economics associated with multiple use. Insulation should always be placed on the outside of massive elements of the building shell rather than on the inside in order to reduce heat losses without isolating the mass from the living space. Concrete floor slabs can contribute to the heat capacity of a building provided they are not isolated by carpets and cushioning pads. Heat losses from the slab can be limited by placing perimeter insulation on the outside of the foundation walls. If the structure is fairly light, the heat capacity can be effectively increased by placing water containers in the interior. A variety of attractive containers are available commercially. An overhang, as illustrated in Figure 1, is used to shade the solar aperture from the high summer sun while permitting rays from the low winter sun to penetrate and warm the inside of the building. In climates having particularly warm and sunny summers, an overhang may not be sufficient to prevent significant aggravation of the summer cooling load. Sky, diffuse, and ground-reflected radiation enter the living space despite the presence of an overhang and must be blocked by external covers or internal shades. Using movable insulation on direct gain apertures has the advantage of reducing nighttime heat losses during the winter, as well as eliminating unwanted solar gains during the summer. Direct gain buildings involve less departure from conventional construction than other types of passive solar systems and are therefore cheaper and more readily accepted by most occupants. However, they are subject to overheating, glare, and fabric degradation if not carefully designed. These problems can be minimized by distributing the sunlight admitted to the building as uniformly as possible through appropriate window placement and the use of diffusive blinds or glazing materials. When properly designed for their location, direct gain buildings provide an effective means of reducing energy consumption for space heating without sacrifice of comfort or aesthetic values. Daylighting is not a passive solar heating technology, but an adjunct to direct gain passive solar buildings that is available year-round. Pleasing uniform illumination can be achieved by using blinds that reflect sunlight toward white diffusive ceilings. The artificial lighting system in many buildings imposes a significant load on the cooling system that may be reduced by daylighting because the fraction of visible light in the solar spectrum is greater than the visible fraction of incandescent or fluorescent lighting. The next system is radiant panels. Radiant panels are simple passive solar systems that are inexpensive and well suited as retrofits, particularly to metal buildings. A sketch of a radiant panel system is presented in Figure 2. Note that the solar aperture consists of one or more layers of glazing material placed over an uninsulated metal panel. The metal panel would ordinarily be a part of the building shell, so that a retrofit is constructed by simply glazing an appropriate area on the south side of the structure. Any insulation or other poorly conducting material should be removed from the inner surface of the glazed portion of the metal panel to facilitate heat transfer to the interior. Figure 2 indicates the fundamental elements of a radiant panel heating system. South-facing apertures with double or triple glazing, a metal panel mounted immediately inside of the south-facing aperture, the thermal storage mass, the insulation in the ceiling and walls, and the overhang as indicated. Solar radiation is absorbed on the outer surface of the metal panel after passing through the glazings. The panel becomes hot and gives up heat to the interior by radiation and convection. Thermal mass must be included inside the building shell as with direct gain systems. Usually only a concrete slab will be available before retrofitting a metal building, and it may sometimes be necessary to add water containers to achieve the desired thermal capacitance. Radiant panels perform on a par with direct gain buildings and are likely to be less expensive when used as retrofits to metal buildings. The next system is thermosiphoning air panels. Thermosiphoning air panels, frequently referred to as TAPs, are also appropriate for use on metal buildings either as retrofits or in new construction. Two configurations occur in practice, and the first, which is referred to as a front flow system, is illustrated in Figure 3. Again, there are one or more glazing layers over an absorbing metal surface, but in this case the metal panel is insulated on the back side. Heat transfer to the interior occurs via circulation vents cut through the metal panel and its insulation at the upper and lower extremes. Solar radiation absorbed on the outer surface of the panel is converted to heat and convected to the adjacent air, which then rises due to buoyancy forces and passes through the upper vent into the living space. The warm air leaving the gap between the inner glazings and the absorber is replaced by cooler air from the building interior that enters through the lower vents. In this manner, a buoyancy-driven loop is established and sustained as long as the temperature in the air gap exceeds that in the living space. Passive backdraft dampers or manually operated vent closures must be employed to prevent reverse circulation at night. Backdraft dampers are usually made of a lightweight plastic material suspended above a metal grid such that air flows freely in one direction but is blocked should the flow attempt to reverse. Figure 3 indicates the fundamental elements of the thermosiphoning air panel system, the front flow version. The second type of thermosiphoning air panel configuration is illustrated in Figure 4 and is called a backflow system. In a backflow system, the flow channel is behind the absorber plate rather than in front of it. An insulated stud wall is constructed a few inches behind the metal panel, and vents are then cut at the top and bottom of the wall. As in the flow channel, thus air in the flow channel thus formed is heated by convection from the back of the absorber plate, and a circulation loop is established in the same manner as in a front flow system. Figure 4 indicates the fundamental elements of the backflow thermosiphoning air panel system. Thermosiphoning air panels have thermal storage requirements similar to those of direct gain and radiant panel systems. Generally speaking, the best performance will be obtained from passive solar systems associated with high heat capacity structures. Although a backflow thermosiphoning air panel performs slightly better than a comparable system in the front flow configuration, the difference is not significant, and construction costs should govern any choice between the two. Both thermosiphoning air panel configurations outperform radiant panels and direct gain systems with comparable glazings and thermal storage mass. This performance edge is due to the low aperture conductance of the thermosiphoning air panels, which can be insulated to arbitrary levels, thereby limiting nighttime heat loss. The next type of system is a thermal storage wall. A thermal storage wall is a passive solar heating system in which the primary thermal storage medium is placed directly behind the glazings of the solar aperture, as illustrated in Figure 5. The outer surface of the massive wall is painted a dark color or coated with a selective surface to promote absorption of solar radiation. Solar radiation absorbed on the outer surface of the wall is converted to heat and conducted, or convected in the case of the water walls, to the inner surface, where it is radiated and convected to the living space. Heat transfer to the living space is sometimes augmented by the addition of circulation vents placed at the top and bottom of the mass wall. These vents function in the same manner as the vents in a thermosiphoning air panel system, except that only a portion of the solar heat delivered by the system passes through the vents. Figure 5 is a schematic indicating the fundamental elements of a thermal storage wall system. A thermal storage wall provides an effective buffer between outside ambient conditions and the building interior. Nighttime heat losses are reduced during the cold winter months, and during the summer unwanted heat gains are limited. This moderating effect generally enables thermal storage walls to outperform direct gain systems. There are many types of thermal storage walls distinguished by the type of storage medium employed. One type of thermal storage wall is called a Trombe wall. It's a thermal storage wall that employs solid, high-density masonry as the primary thermal storage medium. Appropriate thicknesses range from 6 to 18 inches depending on the solar availability at the building site. Sunny climates require relatively thicker walls due to the increased thermal storage requirements. The wall may be vented or unvented. A vented wall is slightly more efficient and provides a quicker warm-up in the morning, but may overheat buildings containing little secondary thermal storage mass in the living space. Another type of thermal storage wall is a concrete block wall. Ordinarily, a thermal storage wall would not be constructed of concrete building blocks because solid masonry walls have a higher heat capacity and yield better performance. However, where concrete block buildings are very common, they may offer opportunities for passive solar retrofits. The south-facing wall of a concrete block building can be converted to a thermal storage wall by simply painting the block a dark color and covering it with one or more layers of glazing. Walls receiving this treatment yield a net heat gain to the building that usually covers the retrofit costs rather quickly. The relatively low heat capacity of concrete block walls is offset somewhat by the large amount of secondary thermal storage mass usually available in these buildings. Concrete floor slabs and massive partitions between zones help prevent overheating and otherwise improve the performance of concrete block thermal storage walls. Concrete block thermal storage walls may also be introduced during the construction of new buildings. For new construction, however, it is advisable to take advantage of the superior performance of solid masonry walls by filling the cores of the block in the thermal storage wall with mortar as it is erected. This process is inexpensive and the resulting performance increment covers the increased cost. The design procedures developed herein are applicable to 8-inch concrete block thermal storage walls with filled or unfilled cores. The next type of thermal storage wall is a water wall. Water walls are thermal storage walls that use containers of water placed directly behind the aperture glazings as the thermal storage medium. The advantage over masonry walls is that the water has a volumetric heat capacity about twice that of high-density concrete, and it is therefore possible to achieve the same heat capacity available in a Trombe wall while using only half the space. Furthermore, a water wall can be effective at much higher heat capacities than a Trombe wall because natural convection within the container leads to a nearly isothermal condition that utilizes all of the water regardless of the wall thickness. The high thermal storage capacity of water walls makes them especially appropriate in climates that have a lot of sunshine. The next type of system is a sun space. There are many possible configurations for a sun space, but all of them share certain basic characteristics. A representative schematic is given in Figure 6. Sunlight enters the sun space through south-facing glazing that may be vertical or inclined or a combination of the two, and is absorbed primarily on mass surfaces within the enclosure. The mass may be masonry or water in appropriate containers and is generally located along the north wall and in the floor. The massive elements provide thermal storage that moderates the temperature in the enclosure and the rate of heat delivery to the living space located behind the north wall. Operable windows and circulation vents in the north wall provide for heat transfer by thermal convection from the sun space to the living space. The north wall may be an insulated stud wall placed behind containers of water or a masonry wall through which some of the heat in the sun space is delivered to the building interior by thermal conduction as occurs in a Trombe wall. A sun space may be semi-enclosed by the main structure such that only the south-facing aperture is exposed to ambient air, or may be simply attached to the main structure along the north wall of the sunroom, leaving the end walls exposed. The schematic here indicates the fundamental elements of a sun space. The temperature in a sun space is not thermostatically controlled, but is generally moderate enough for human habitation during most of the day and appropriate for growing plants year-round. Amenities are thus provided that compensate for the somewhat higher cost of sun spaces relative to other types of passive solar heating systems. Now a few comments on incremental cooling load. Unfortunately, not all of the heat delivered to the living space by a passive solar heating system is useful to the occupants. During the winter heating season, part of the delivered solar energy will cause the building to overheat unless ventilation is employed to limit the indoor temperature. It is to be expected that some overheating will occur in most passive solar buildings, but too much excessive heat is indicative of a poor design. It may be that the solar aperture is too large or that inadequate thermal storage mass has been provided. During the summer cooling season, a passive solar heating system continues to function, although the increased solar elevation angle reduces the radiation flux transmitted through the glazings, particularly if an overhang is employed. However, all heat delivered to the building during the cooling season is unwanted and must be removed either by ventilation or by evaporative or vapor compression cooling systems. A poorly designed passive heating system can significantly aggravate the summer cooling load of a building. The sum of all unwanted heat delivered to a building by the passive heating system is referred to as the incremental cooling load. This is clearly an important parameter because it represents the cooling penalty associated with various passive solar designs. Now we will look at climatic considerations. These are characteristic weather parameters, climate and conservation measures, solar availability, and then some guidelines for schematic design. First, we will look at the characteristic weather parameters. This discussion is based on two weather parameters that in certain combinations may be used to characterize climates with respect to the potential effectiveness of conservation and passive solar measures in reducing energy consumption for space heating. The first of these important parameters is the heating degree days, which is represented by the symbol DD and has units of degrees Fahrenheit day. Degree days is calculated by summing the difference between the base temperature and the outside ambient temperature over each hour in the time period of interest and dividing the result by 24 hours per day. All negative terms are omitted from the sum. The base temperature is the thermostat's set point adjusted to account for the presence of internal heat sources. The time period of interest is usually 1 month or 1 year. This method of calculating degree days differs from the American Society of Heating, Refrigerating, and Air Conditioning Engineers ASHRAE approach and is recommended because it yields better accuracy when applied to the analysis of passive solar buildings. Furthermore, the hourly data required for such a calculation is available in the typical meteorological year database. The heating degree days is an important weather parameter because the amount of heat lost from a building during a particular time period is directly proportional to degree days. That is, if a building is moved from one location to another having twice as many degree days, the heat loss from the building will double. The second important weather parameter is called VT2. This is the amount of solar energy transmitted through a vertical south-facing double-glazed aperture during a specific time period. The V in VT2 stands for vertical, the T indicates transmitted radiation, and the 2 represents the 2 glazing layers. The parameter VT2 is important because it quantifies the solar resource available for passive space heating. In the following discussion, combinations of VT2 and DD are used to characterize climates with regard to the relative importance of conservation and passive solar measures for reducing auxiliary heat consumption in buildings. Now, the second characteristic weather parameter is the climate and conservation measures. The fraction of the monthly heating load of a building that can be met by passive solar strategies depends on certain characteristics of the building design and, for double-glazed systems, which are by far the most common, on the ratio VT2 divided by DD. For this discussion, it is sufficient to know that the parameter VT2 divided by DD provides an accurate measure of the passive solar potential of a given climate during any selected month. It follows that by considering the value of VT2 divided by DD for each month in the heating season, It's possible to assess the passive solar potential of the climate for the full annual cycle. One way to do this might be to average VT2 divided by DD over all months in the heating season, but that approach would ignore the fact that it is more important to have high solar heating fractions in cold months with high values of DD than it is in warm months with low values of DD. The solution to this dilemma is to determine the degree-day weighted average of VT2 divided by DD. It follows that in climates having low values of weighted average of VT2 divided by DD, conservation measures such as insulation, storm windows, weather stripping, etc., will be more important than in climates having high values. If only a small portion of the building load can be displaced with solar energy, then reduction of that load through the use of conservation measures clearly becomes a top priority. A map of the continental United States with contours of constant weighted average of VT2 divided by DD is presented in Figure 7, which you will see in a moment. The three contour lines divide the map into 4 climate regions that are referred to as mild, moderate, harsh, and very harsh. General descriptions of these climate regions and qualitative comments regarding regionally appropriate design are presented in the next 4 subsections. Figure 7 indicates these principal climate regions. Mild climate regions, naturally, one would expect they are on the southern rim of the U.S. Moving north, you move into a moderate band, then a harsh band, and then the very harsh climate region is in the northern states and northeast states. First, some comments on passive solar considerations in mild climates. The mild climate region includes the southern third of California and Arizona, small parts of the southern extremes of New Mexico, Texas, and Louisiana, and most of the Florida Peninsula. In the mild region, the winter heating load varies from small to nil, and in any case there is plenty of sunshine available to meet whatever loads do arise. Generally, the small heat loads can be displaced with inexpensive radiant panels or direct gain systems having relatively small solar collection apertures. However, summer cooling loads in this region can be quite high, usually exceeding the winter heating load several times over. It's therefore particularly important to assure that the incremental cooling load associated with the passive heating system does not negate the small savings realized during the winter heating season. The use of defensive countermeasures such as adjustable shades and shutters that shield the solar aperture from direct and diffuse sunlight during the cooling season is essential. The term defensive cooling refers to strategies or devices that prevent excess heat from entering a building, in contrast to procedures for removing such heat, as with air conditioning equipment after it has gained entry. Because of the high solar heat gain factors obtainable in the mild region, conservation measures are not as important as in regions further north. Now some comments on passive solar considerations in moderate climates. The moderate region includes most of California, the southern half of Nevada, the central third of Arizona, and most of New Mexico, Texas, Louisiana, Mississippi, Alabama, Georgia, and South Carolina. The Florida Panhandle and most of the North Carolina coast are also included. Thermal storage walls, sun spaces, thermosiphoning air panels, and direct gain systems are all typically appropriate in this region. The solar apertures will be larger than in the mild region, and more thermal insulation will be required. Defensive cooling strategies are also important to overall performance. Now some comments on passive solar consideration in the harsh climates. The harsh region includes most of Washington, Oregon, Idaho, Nevada, Wyoming, Utah, Colorado, Nebraska, Kansas, Oklahoma, Missouri, Arkansas, Kentucky, Tennessee, Virginia, and North Carolina. It also includes northern parts of Arizona, New Mexico, Texas, Mississippi, Alabama, Georgia, and South Carolina that are also included, as well as southern parts of Montana, South Dakota, Iowa, Illinois, Indiana, and West Virginia. Finally, the harsh region includes coastal areas in Massachusetts, Rhode Island, New York, New Jersey, Maryland, and all of Delaware. At the northern extremes of the harsh region, night insolation should be considered on direct gain apertures. Otherwise, all passive systems may be adequate in this region. Heating loads are substantial, making conservation measures very important. Despite the heating loads, defensive cooling strategies are still required to assure positive net energy savings. Now, some brief comments on climate and conservation measures in the very harsh climates. The very harsh region includes all of North Dakota, Minnesota, Wisconsin, Michigan, Ohio, Vermont, New Hampshire, and Maine, most of Montana, South Dakota, Iowa, Illinois, Indiana, West Virginia, Connecticut, Pennsylvania, and Massachusetts, and parts of Washington, Idaho, Wyoming, Nebraska, Kentucky, Virginia, Maryland, New Jersey, and Rhode Island. Near the boundary between the harsh and very harsh regions, or in areas with greater than average sunshine, direct gain systems without night insulation may still be viable, provided the aperture is kept fairly small. Thermal storage walls and sun spaces will function well in this region, although night insulation may be desirable near the northern boundary. Thermosiphoning air panels are a good choice because arbitrarily high levels of fixed insulation can be placed between the collector surface and the living space. Heavy use of conservation measures is critical to performance in the very harsh region. Defensive cooling strategies, though less of a concern than in the regions with milder winter climates, should not be ignored. Now we will talk about the importance of solar availability. As previously discussed, the parameter VT2 provides a measure of the availability of solar radiation as a space heating resource during a specified time period. If VT2 were evaluated for the duration of the winter heating season, the result would provide some indication of the potential of the site for passive solar heating applications. However, it is more important to have high solar availability during the colder months of the heating season than during the warmer months, and the straight summation involved in evaluation of VT2 does not reflect this fact. A better measure of the effective solar availability is obtained by taking the degree day weighted average of the monthly VT2s that occur during the heating season. A map of the continental United States with contours of constant weighted average of VT2 is presented in Figure 8. The four contours divide the map into 5 regions that are labeled most sunny, very sunny, sunny, cloudy, and very cloudy. These 5 regions cut across the 4 principal climate regions defined in Figure 7 and form subregions that are related to the appropriate size of solar apertures. As a general rule, the sunnier subregions of a particular principal climate region should have the larger solar apertures. Figure 8 indicates the solar availability regions ranging from very cloudy, cloudy, sunny, very sunny to most sunny. First, some comments on solar availability in the most sunny regions. This region is limited to the desert southwest and includes major parts of Nevada, Arizona, and New Mexico. Subregions in which the most sunny region overlaps the harsh region are ideal for passive solar heating because of the coincidence of a substantial heating load and excellent solar availability. The most sunny, moderate subregion is also quite good for passive solar heating. Now some comments on solar availability in the very sunny region. The very sunny region forms a complex crescent in the mountain, Pacific, and Plains states and contains parts of California, Nevada, Utah, Colorado, Arizona, South Dakota, Texas, Oklahoma, Kansas, and Nebraska. It forms a large, very sunny, harsh subregion in which passive solar applications are very beneficial. Now some comments on solar availability in the sunny region. The sunny region forms a still larger crescent about the very sunny region. It includes parts of Florida, Alabama, Georgia, South Carolina, North Carolina, and Virginia. The sunny area cuts completely across the country from north to south and forms subregions with all four principal climate zones. A broad range of passive solar designs is viable across these subregions. Now some comments on solar availability in cloudy regions. The cloudy region traverses the country from north to south and forms four types of subregions, among which many passive designs are feasible. Parts of the Pacific Northwest, the Midwest, and the Eastern Seaboard are included in the cloudy region. Now some comments on the very cloudy region. The very cloudy region includes only the extreme Pacific Northwest and the central to eastern Great Lakes area. The Great Lakes area, where the very cloudy region overlaps the very harsh region, is the poorest location in the continental United States for passive solar heating. The Pacific Northwest area overlaps the harsh climate region and is slightly better suited for passive solar applications. Now some guidelines for schematic design. We will look at guidelines for schematic design that are related to the climate regions appearing in figures 7 and 8 and discussed above. The objective during schematic design is to develop a rough idea of what the final building will be like. The designer is not concerned with details at this point, but seeks only to establish the basic shape, dimensions, materials, window areas, and insulation levels that will characterize the design in these procedures. The characteristics of the passive solar heating system are added to the list of more traditional architectural concerns. Passive solar buildings are usually elongated in the east-west direction so that a large south-facing surface is presented to the low winter sun for solar heating, and small east and west-facing surfaces are presented to the northerly rising and setting summer sun to reduce unwanted solar gains. The aspect ratio, east-west dimension divided by north-south dimension, should be at least about 5/3. Ideally, passive solar buildings should be no more than 2 zones deep in the north-south direction. The 2-zone limit on depth generally allows solar heating collected on the south side of the building to be transported for use to the north side, thereby improving thermal performance. Multi-story buildings are well suited to passive solar design, particularly if the above recommendations on aspect ratio and depth are observed, because of the large vertical surface that may be presented to the winter sun for solar absorption. Orientations that depart from true south by up to 30 degrees are permissible. Performance penalties will usually be less than 10%. An easterly bias is preferred in applications that require a rapid warm-up in the morning, whereas a westerly bias will sometimes improve the performance of buildings that are occupied in the evening because of the improved phasing of heat source and heat load. Windows not facing south should be kept small while complying with local building codes. Particularly in the colder climates, it's best to place most of the non-south window area on the east or west side of the building to take advantage of winter solar gains available during the early morning and late afternoon. All windows, including those facing south, should have at least 2 glazing layers, and in the harsh and very harsh regions, triple or even quadruple glazing should be considered. Especially in the warmer climates, drapes, or better still, movable opaque covers or shades, as described as thermal shutters and shades, are recommended as means to prevent unwanted sunlight from entering the windows during the summer. The interaction between a passive heating system and its environment is a complex process that involves many subtle phenomena. The complexity of the interaction makes it difficult to determine exactly what type of passive system will perform best in a given climate. Ultimately, detailed design analysis calculations may be required to make the final decision. However, a few generalizations may be cited that are useful for selecting candidate systems during the schematic phase of design. The general rules for system selection are based on the steady-state conductance of the passive solar aperture. The aperture conductance is the amount of heat that would be lost through the solar aperture if the outside ambient temperature were maintained at 1 degree Fahrenheit below the indoor temperature for a period of 1 hour. It's generally true that systems with low values of steady-state conductance are better suited for use in areas having relatively severe winter climates than are systems with larger aperture conductances. The climate regions based on the importance of conservation measures that are illustrated in Figure 7 provide a convenient measure of winter's severity. The selection process based on aperture conductance may be further refined by the observation that it is also more important to have a small steady-state conductance in regions that receive relatively little sun. The solar availability contour map in Figure 8 is useful in making this secondary assessment. In summary, passive solar systems having low aperture conductances are recommended for use in regions having severe winter climates with little sunshine. With regard to the sizing of the overhang, this is an important consideration, of course. The purpose of a fixed overhang is to reduce unwanted solar gains during the summer while allowing the low winter sun to eliminate the solar aperture and provide heat to the building interior. Sizing an overhang is a difficult problem because the heating season is not symmetrical about the winter solstice but tends to be displaced toward the new year. Therefore, a design that provides adequate protection from overheating in the fall may tend to reduce the amount of solar energy available for needed space heating in late winter or spring. Since an overhang does not provide protection from sky diffuse or ground reflected radiation, it is often necessary to provide additional countermeasures to prevent overheating during the cooling season. For this reason, the currently accepted design practice is to size an overhang such that the performance of the passive heating system is minimally affected and employ additional countermeasures against overheating as required. Starting point values for thermal insulation are recommended on the basis of principal climate region and building size and geometry. The R values, that is the thermal resistance of walls, including installed insulation and other layers, should lie in the intervals consistent with the intervals indicated in Figure 9. Figure 9 indicates principal climate regions and their associated R values, thermal resistance values. Larger buildings derive a greater benefit from incidental heating by internal sources because of the reduced external surface area relative to the heated floor area. For 3 reasons, it's common practice to employ higher levels of insulation in the ceiling than the wall. First, it's cheaper to insulate the ceiling than the wall. Second, stratification causes larger heat loss rates per unit area of ceiling than per unit wall area. And third, solar gains on roofs during the summer can cause unwanted heating of the living space beyond that caused by high ambient air temperature. With regard to insulation levels, the heat losses through the building perimeters and fully bermed basement walls are limited by contact with the soil so that insulation levels need not be so high as for exposed external walls. Ordinarily, floors are not insulated so as to ensure that pipes located below do not freeze. Because of widely varying conditions beneath ground level floors, it's difficult to recommend specific insulation levels. The insulation levels recommended above are intended only as starting point values. Design analysis calculations must be performed before fixing any important design variables. With regard to infiltration, many older buildings have infiltration rates as high as 1.5 air changes per hour. A reduction to 1 air change per hour may be achieved by employing a plastic vapor barrier. Taking care to seal all joints and foam any cracks will generally further reduce the infiltration rate to 0.5 air changes per hour. It is strongly recommended that the infiltration rate be limited to 0.5 air changes per hour for both new construction and retrofits whenever possible. Since extremely low rates may be hazardous to the occupant's health due to the accumulation of indoor pollutants, further reductions in infiltration heat loss should be attempted only through the use of window heat recovery units. Extensive use of these units can yield effective infiltration rates as low as 0.187, and under certain circumstances, the additional expense involved may be justified. With regard to the solar collection area, the solar collection area indicated are intended to illustrate starting point values for a design analysis procedure. Figure 10 is an example of solar aperture area in percent of floor space. Remember, this is only for illustration purposes. Large apertures occur where high solar availability coincides with a large heat load. Small apertures occur where the solar availability is low or the heat load is small. These aperture sizes used in conjunction with the recommended insulation and infiltration levels will yield a payback period of 10 years for some systems. Figure 10 indicates the solar aperture area in percent of floor space for the continental United States for one type of system. The amount of thermal storage mass required per square foot of solar aperture depends primarily on the solar availability at the building site. The relative solar availability in the continental United States is given by the contour map in Figure 8. Masonry thermal storage walls and sun spaces with masonry common walls generally employ a wall thickness of about 12 inches of high-density material. This thickness is quite appropriate in the sunny region and to a large extent in the adjacent cloudy and very sunny regions. However, in the most sunny region, a wall thickness of 18 inches should be employed to protect against overheating and fully utilize the available resource. In the very sunny region, wall thicknesses may range from 12 inches to 18 inches, depending on which boundary the building site is nearest. At the other extreme, mass walls in the very cloudy region need only be 6 inches thick, and in the adjacent cloudy region, thicknesses may range from 6 to 12 inches depending upon position relative to the boundaries. When water containers are used for thermal storage, either in sun spaces or thermal storage walls, equivalent thicknesses comparable to those recommended for masonry walls are appropriate in all solar availability regions. However, because the heat capacity of water is roughly twice that of high-density masonry, significant downward revisions may be permissible. Direct gain apertures, radiant panels, and thermosiphoning air panels all use interior mass for heat storage. Ideally, the interior mass should have a high density and be distributed in thicknesses of 2 inches to 6 inches. Appropriate area ratios are 3 in the very cloudy region, 3 to 6 in the cloudy region, 6 in the sunny region, 6 to 9 in the very sunny region, and 9 in the most sunny region. Equivalent or somewhat smaller volumes of water may be used instead of masonry in lightly constructed buildings. Here is a publication that you may find helpful for the detailed design of your building. It can be obtained from the Defense Technical Information Center. This is an abstract of the publication, which indicates that the energy efficiency of buildings can be greatly improved through the use of passive solar heating strategies. These strategies may be applied to many existing buildings that are suitable for retrofit and are universally applicable to new construction. The purpose of this design procedure is to provide the tools required by professionals and who are involved in building design and or evaluation who wish to improve the energy efficiency of buildings by use of passive solar heating. 3 types of tools are used. First, a general discussion of the basic concepts and principles of passive solar heating is presented to familiarize the reader with this relatively new technology. Second, a set of guidelines are presented for use during schematic design that will enable a user to quickly define a building that will perform in a cost-effective manner at the intended building site. And finally, a quantitative design analysis procedure is presented that provides the user with an accurate estimate of the auxiliary heating requirements of a given passive solar design. This procedure is presented that provides the user with an accurate estimate of the auxiliary heating requirements of a given passive solar design. This procedure may be used to refine or fine-tune a preliminary design based on the schematic design guidelines, or may be used during proposal evaluation to compare the merits of various candidate designs. Another useful design phase publication is available through the National Technical Information Service. It is also a Department of Defense production, but do not be concerned about that. It is just good solid engineering technical guidance in this area. Here on this slide are some additional resources that you may find useful to you moving forward. And here are some useful analytical tools to analyze the performance of small residential type skin load dominated passive solar heated buildings. Suggested use is guidelines for home building with Builder Guide software. This is a simple computer software tool in a Windows format for evaluating the solar savings fraction of a building design, and the program is available from the Sustainable Buildings Industry Council. To analyze the performance of small residential, institutional, and commercial passive solar heated buildings with 1 or 2 thermal zones, suggested use is Passive Solar Design Strategies Guidelines for Home Building and Energy 10 software. The solar heating performance of simple commercial buildings of up to approximately 10,000 square feet can be evaluated using the strategies and the Energy 10 hourly simulation program. To analyze the performance of large internal loaded dominated commercial and institutional buildings, refer to DOE 2 or the latest version. The solar heating performance of large and more complex buildings requires the use of a more powerful computer program. Multi-zone programs developed by the government, by the Department of Energy, such as DOE 2.1 and Energy Plus, are available from the Simulation Research Group of the Lawrence National Laboratory. Now, a few brief rules of thumb for concept design phase use. South-facing passive storage walls in direct sunlight should have a minimum of 30 pounds water storage or 150-pound masonry concrete storage per square foot of south vertical glazing. If the storage media is not located in direct sunlight, 4 times this amount will be needed. Other recommendations, at least 5 to 6 gallons of water storage, about 45 pounds per square foot of south glass. Shading of south windows should be used to reduce summer and fall overheating. One effective geometry is a roof overhang, which will just shade the top of the window at noon solar time, sun elevation of 45 degrees, and will fully shade the window at noon sun elevation of 78 degrees Fahrenheit. The best thickness of a Trombe wall is 12 to 16 inches. The masonry should have a high density, at least 100 pounds per cubic foot. Thermal circulation vents can be used to increase daytime heating, but will not increase nighttime minimums. Vents should have lightweight passive backdraft dampers or other means of preventing reverse flow at night. 2 to 3 square feet of south-facing double glazing should be used for each BTU per degree Fahrenheit day of additional thermal load exclusive of the glazing. This will give 70 to 80% solar heating in northern New Mexico as an example for a building kept within the range of 65 to 75 degrees. For a well-insulated space in 40-degree north latitude in cold climates, outdoor temperature 20 degrees Fahrenheit to 30 degrees Fahrenheit. The ratio of south glazing to floor area is in the range of 0.20 to 0.25 to maintain an average space temperature of 68 degrees over 24 hours. A 200 square foot floor space needs 40 to 50 square feet of south glazing. In temperature climates of 35 to 45 degrees Fahrenheit, outdoor temperature use ratios in the range of 0.11 to 0.17. For greenhouses, to determine solar gain, the solar heat gain factor is 1200 BTUs per square foot of glazing per clear day. S is equal to 700 BTUs per square foot per average day. Double glaze only south walls. Insulate all opaque surfaces to R20. Outside foundation to frost line to R10. Minimize infiltration with caulking. Thermal mass should equal 5 gallons of water or 1 2/3 cubic foot of gravel per square foot of glazing. If storage is thermally isolated from greenhouse, air should be moved at 10 cubic feet per minute per square foot of glazing through the storage. And that brings us to the conclusion of this brief discussion of passive utilization of solar energy to heat buildings. I hope this has been of some interest to you and was about what you were looking for. It is strictly an introductory discussion, but will hopefully give you what you need to move forward and address passive solar heating issues as they come across your desk with projects in the future. With that, again, thank you very much for letting me chat with you, and have a nice rest of the day.